Right now, in France, nuclear reactors capable of feeding millions of homes are being forced to slow down, not because the reactors have run out of fuel, not because engineers have lost control, but because the rivers beside them have become too hot to carry the heat away. Reuters reported that French nuclear output was cut by about 4.1 gigawatts during the heatwave, roughly 7% of national electricity demand at midday. That is the first shock. One of the most powerful energy systems in Europe, a fleet built to run through winter storms, market panic, fuel shocks, and political crises, can still be brought down by something as ordinary as river water. But that is not the most frightening part. The frightening part is that this is not a breakdown in the usual sense. It is a boundary. The machines may still work, the fuel may still be there, the grid may still be stable, but the natural system around the machine is beginning to say no. And that changes the question. The question is no longer simply how many reactors France can build, restart, or maintain. The question is how much heat the landscape around them can absorb in a climate where summer arrives earlier, stays longer, and pushes rivers toward temperatures that used to belong to exceptional years. If this video reaches someone living near a river, a power plant, a hot city, or a home where the air conditioner has become a survival device, liking, subscribing, and leaving a comment with that location helps show where this hidden limit is no longer abstract, because the story begins beside a river, and the river is warming. On the map, the French nuclear fleet looks like a system of confidence. Reactors are spread across the country, some near the coast, many beside rivers, tied into one of the most nuclear-dependent grids in the world. For decades, that map has carried a simple promise. When France needs electricity, its reactors can provide a steady base. They do not wait for wind. They do not wait for sun. They do not burn coal on site. They turn heat into steam, steam into motion, and motion into electricity. The whole arrangement seems solid, almost geological. Concrete domes, cooling towers, turbines, transmission lines, control rooms, operators watching screens through the night. But during a heatwave, the most important part of that system may not be the dome. It may be the river outside the fence. At Golfish, on the Garonne, at Bougy and Saint Alban, near the Rhône, at Nogent-sur-Seine, beside the Seine. At other plants across the country, the same quiet tension appears in different forms. The plant is not only producing electricity, it is producing waste heat. Every thermal power station does. Coal plants do it, gas plants do it, nuclear plants do it. The useful electricity is only part of the energy story. The rest must go somewhere. For many nuclear reactors, that somewhere is water. Water takes heat from the condenser. Water carries heat through pipes, channels, towers, or discharge systems. Water receives what the turbine no longer needs. On a normal day, this is routine. On a hot day, it becomes a negotiation. The plant needs the river, but the river is already under stress. The river has fish, insects, algae, sediment, bacteria, plants, farmers, boaters, towns, drinking water systems, irrigation intakes, and ecosystems that have evolved inside a range of temperatures. A river is not a pipe. It is a living corridor. When it is already warm, adding more heat is not neutral. It can reduce oxygen in the water. It can stress fish. It can shift ecological thresholds. It can turn a narrow industrial problem into an environmental one. That is why France does not simply allow unlimited hot water to be sent back into rivers. The nuclear regulator and environmental rules set limits for discharge temperature and for how much warmer the water can become downstream. When those limits are approached, EDF has to reduce reactor output, or in some cases temporarily shut a unit down. That is what makes this event different from the familiar stories people tell about energy. The image of a nuclear crisis usually involves radiation, explosions, evacuation zones, or emergency sirens. This story is quieter. There is no cinematic plume. There is no reactor runaway. There is no sudden loss of control. There is a spreadsheet of temperatures. There is an environmental permit. There is a measured river, upstream and downstream. There is a threshold that says the plant cannot keep pushing the same amount of heat into the same water. The drama is bureaucratic, but the meaning is physical. The law is only writing down what the river can no longer hide. In the middle of a heat wave, people experience electricity from the demand side. They feel the room getting hotter. They hear the hum of a fan. They see air conditioners dripping on city streets. Hospitals try to keep wards cool. Care homes try to protect elderly residents from heat that becomes dangerous when the night does not cool down. Data centers continue running. Trains need signals. Supermarkets need refrigeration. Pharmacies need cold storage. Water systems need pumps. Apartment blocks need elevators. The hotter it gets, the more the modern world leans on electricity. Yet at the same time, some power stations lean on water that is losing its ability to cool them. This is the double pressure. Heat increases demand and constrains supply. It pushes from both ends. In ordinary energy planning, those two pressures are often treated separately. Demand planners ask how much air conditioning will be needed. Plant operators ask how much capacity is available. Grid managers balance flows, but a heat wave connects the equations. The same hot air that makes homes intolerable also warms rivers. The same dry spell that increases wildfire risk can reduce river flow. The same clear skies that increase solar production can coincide with low wind and extreme cooling demand. The system is not facing one stress. It is facing a pattern. That is why this story matters beyond France. France is a special case because nuclear power plays such a large role in its grid, but the hidden limit is not French. Thermal power needs cooling. Hydropower needs water. Cities need electricity to survive heat. Crops need irrigation in drought. Rivers are asked to cool reactors, feed farms, dilute pollution, support ecosystems, and supply towns at the same time. In a cooler climate, the overlap was manageable more often. In a hotter climate, the overlap becomes conflict. The first people to feel it may not be engineers. They may be patients in overheated hospitals, train passengers delayed by infrastructure strain, workers sent home during peak heat, farmers watching irrigation restrictions tighten, or families whose electricity bills rise as wholesale prices jump. But behind those human scenes is a simple physical fact. Heat has to move from one place to another. Electricity production does not erase heat. It redistributes it. And when the receiving environment is already hot, the margin narrows. The headline number is 4.1 gigawatts. It is easy to say quickly and easy to underestimate. A gigawatt is 1 billion watts. 4.1 gigawatts is 4,100,000,000 watts of electrical capacity no longer available at that moment. It is not a small adjustment hidden in the noise. It is the scale of several large power stations. It is enough to matter to the market. It is enough to show up in grid data. It is enough that Reuters compared it to about 7% of total French power demand at midday during the event. 7% may sound manageable, and in one sense it was. The French grid did not collapse. RTE, the grid operator, said supply remained secure. Solar generation helped during the daylight peak. Other plants continued operating. France could rely on grid management, imports, exports, market signals, and reserve planning. But the point is not that one hot day destroyed the system. The point is that one hot day exposed where the system is thin. Energy security is often discussed as a problem of fuel and finance. Does the country have enough gas? Enough uranium? Enough wind turbines? Enough solar panels? Enough storage? Enough transmission? But this event adds another question. Is there enough cold? Not cold as a luxury. Cold as infrastructure. Cold river water. Cool nights. Soil moisture that allows landscapes to moderate heat. Reservoir levels that keep flows stable. Air temperatures low enough for equipment to shed heat efficiently. Cold is not usually counted as a resource until it disappears. Then, it becomes visible everywhere. In a nuclear plant, the conversion of nuclear heat into electricity depends on a temperature difference. The reactor creates heat. The turbine system converts part of that heat into useful work. But the rest must be rejected to a cooler sink. The colder the sink, the easier it is to condense steam and keep the thermodynamic cycle efficient. The warmer the sink, the more difficult the cycle becomes. This is not a political opinion. It is basic physics. Every heat engine needs a hot side and a cold side. The bigger the useful difference between them, the more effectively it can work. When the cold side warms, the machine can still run, but its margins shrink. In France, during the heatwave, the issue was not simply efficiency. It was environmental compliance. If river water is already close to a temperature limit, the plant cannot keep adding heat at the usual rate without exceeding rules designed to protect downstream ecosystems. So output is reduced. Less output means less waste heat. Less waste heat means the discharge can remain within limits. The reactor becomes adjustable not because the atom has changed, but because the river has. This is the hidden inversion. People often imagine nuclear power as independent of weather, because it is not visibly weather-driven. It does not need wind speed or sunlight, but it is still embedded in a physical environment. It needs cooling water, or cooling air, or cooling towers, and those systems perform differently during extreme heat. A reactor is not floating outside climate, it is anchored inside it. The extreme number is not only the power cut, it is the temperature context around that cut. Meteo France reported that June 2026 became the hottest June ever recorded in France, with a national average temperature of 22.7 degrees Celsius, 3.8 degrees Celsius above the reference average. During the episode, parts of France exceeded 40 degrees Celsius. Meteo France also reported record hot afternoons and an exceptionally hot night during the peak of the heat wave. Those details matter because the river does not respond only to the afternoon maximum. It responds to days of accumulated heat. A short spike can be absorbed more easily. A prolonged heat wave changes the entire background state. Warm air heats the water surface. Low flows reduce dilution. Warm nights prevent recovery. Dry soils reduce evaporative cooling. The river enters the day already compromised. It is not a glass of cold water into which heat can be poured. It is a glass that has been sitting in the sun. That is the comparison people can feel. Imagine trying to cool a hot pan with water from a tap. If the tap water is cold and flowing quickly, the pan cools fast. If the tap water is already warm and coming out slowly, the same pan stays hot longer, and the water itself heats quickly. A nuclear plant is vastly more complex, but the principle is not mysterious. It needs a sink for heat. When the sink warms, the system loses room to maneuver. The headline number shocks because it translates climate into power. 4.1 gigawatts is not a temperature record. It is not a weather map. It is a piece of national infrastructure stepping back because the landscape around it has crossed a line. That is why the number should not be read as a failure of one company or one technology alone. It is a signal of coupling. The power system, the water system, the health system, the climate system, and the ecological system are not separate compartments. They touch through small thresholds: a permit temperature, a river flow, a nighttime minimum, a megawatt margin, a hospital cooling load, a transformer rating, a fish kill threshold, a household bill. When the heat rises, those thresholds begin to line up. The event becomes more than a story about electricity. It becomes a story about the architecture of modern life. The part that is easiest to miss is also the part that matters most. This is not primarily a story about a dangerous reactor. It is a story about an overloaded heat sink. Not the reactor, but the river. Not the fuel, but the discharge. Not the iconic dome, but the invisible temperature difference between upstream and downstream. That distinction is essential because it keeps the story honest. Nuclear reactors are designed with safety systems that manage reactor heat, emergency cooling, shutdown procedures, backup power, and accident scenarios. Those safety questions are real, but they are not the central mechanism here. In this case, the issue is that normal operation produces waste heat, and environmental rules limit how much of that heat can be returned to rivers under hot conditions. ASNR. The French Nuclear Safety Authority has explained in its public material that when upstream water temperature is too high, EDF must reduce reactor power or even shut down a reactor in order to respect downstream temperature limits. That sentence is the whole hidden story. It means the plant can be technically capable and still be environmentally constrained. It means output can fall without a mechanical failure. It means climate pressure can enter through regulation because regulation is standing guard for biology. The river is not just scenery, it is part of the plant's operating envelope. A nuclear power station beside a river is sometimes described as if the river is merely a supply line. Water comes in, water goes out, but the river is also a receiver of consequence. It receives heat. It carries that heat through habitat. It carries it past spawning grounds, algae growth zones, oxygen-sensitive species, and downstream users. Warm water holds less dissolved oxygen than cold water. Many aquatic organisms are sensitive not just to absolute heat, but to sudden changes, duration, and the timing of heat relative to life cycles. A fish may survive one afternoon of warm water, but struggle through several days when night brings no relief. An ecosystem can tolerate a pulse, but not always a plateau. That matters because heat waves increasingly behave like plateaus. They do not simply peak, they sit. The old assumption was that the environment would reset between extremes. A hot day would be followed by a cooler night. A dry week would be followed by rain. A warm river would recover. But the new pattern often removes the reset. Hot nights keep water warm. Dry soils feed back into hotter afternoons. Blocking high pressure can hold the same air mass in place. Rivers enter each day with less recovery than the day before. For a power plant, that means the margin is not only a question of how hot the afternoon becomes, it is a question of how long the system has been accumulating heat. This is why the phrase hot rivers can be misleadingly simple. A hot river is not only warmer water, it is reduced carrying capacity. It is a smaller thermal budget. It is a cooling account with less balance remaining. The plant can withdraw from that account only until the rules say the river's ecological balance would be overdrawn. And when that happens, output falls. The simple story would say France had a heat wave and nuclear plants reduced power. The deeper story says a hotter climate is shrinking the thermal space within which some power plants can operate at full capacity. That space is invisible because nobody sees it until the numbers move. A river at 20 degrees and a river at 28 degrees may look similar from a bridge. The surface may shine the same. Boats may pass. Grass may grow along the bank. But inside the plant's calculations, they are different worlds. The colder river can absorb more heat before limits are reached. The warmer river cannot. The colder river is a buffer. The warmer river is a warning. And when the river is low, the warning sharpens. Flow is as important as temperature. A large volume of moving water can dilute heat more effectively than a slow, shallow river. In drought, less water carries the same ecological burden. The same discharge has a larger effect. The river becomes both warmer and smaller as a cooling system. That is the double loss. Not only does the water begin hotter, there is less of it to share the heat. This is why heat and drought together are so powerful. A heat wave alone can stress the river. A drought alone can reduce flow. Together, they turn a cooling system into a bottleneck. This bottleneck does not look dramatic from the outside. The cooling towers may still stand. The transmission lines may still hum. The control room may be calm. But the operating decision has already changed. The power station has entered a zone where environmental protection and electricity demand pull in opposite directions. Reduce output, and the grid has less electricity during a time of high demand. Continue output, and the river receives more heat during a time of ecological stress. That is not a slogan, it is a real trade-off. And it is a trade-off that becomes more frequent when extreme heat becomes more frequent. This is the buried lesson of the event. Modern infrastructure was not built in a vacuum. It was built inside a climate baseline. Engineers used historical records. Planners looked at river flows, heat extremes, demand peaks, seasonal patterns, safety margins, and recurrence intervals. Those assumptions were not foolish. They were the best available world at the time. But climate change shifts the baseline beneath those assumptions. What was once rare can become repeated. What was once late summer can appear earlier. What was once a few dangerous afternoons can become a multi-day or multi-week stress test. The equipment may not suddenly fail. Instead, the operating envelope tightens. The system becomes more conditional. It can still work, but not always at the same output. Not always with the same margin. Not always under the same rules. This is a more unsettling story than sudden collapse, because it is easier to ignore. Sudden collapse forces attention. Narrowing margins invite delay. They allow officials to say the grid is secure, which may be true. They allow operators to say the reactors are safe, which may also be true. They allow the public to move on when the heatwave passes. But the margin has spoken. The river has shown that the old background can no longer be assumed. To understand the mechanism, the viewer has to follow heat, not electricity. Electricity is the clean output people notice. Heat is the shadow output that has to be managed. Inside a nuclear reactor, atoms of uranium split. That process releases energy as heat. The heat warms water in the reactor system, directly or indirectly, depending on the reactor design. That heat produces steam. The steam spins a turbine. The turbine drives a generator. The generator sends electricity into the grid. Up to this point, the story feels like a triumph of control. Atoms, metal, steam, magnetism, power lines. But after the steam has done its work, it must become liquid again. It has to be condensed, so the cycle can continue. Condensing steam requires removing heat from it. This is where the cooling system enters. In some plants, river water may be used in a once-through system, taking in large volumes and returning them warmer. In others, cooling towers reduce river withdrawals by releasing much of the heat into the air through evaporation. Though they still need make-up water and still interact with weather, different sites have different designs, permits, rivers, and constraints. But the principle remains. The power station needs a cold side. Without a cold side, the cycle becomes less efficient or impossible to operate within limits. The central mechanism is called thermal discharge limitation. It sounds technical, but it can be explained in a kitchen. A person boils a pot and wants to cool it. The fastest way is to put it near something cooler, like cold water or cold air. If the room is already hot and the water is already warm, cooling takes longer. If the person pours hot water into an aquarium, the fish may be stressed or killed. So there is a rule. The water can only be warmed so much. A nuclear plant is doing a vastly scaled version of this. It is not dumping boiling reactor water into a river. It is transferring heat through industrial systems, cooling circuits, condensers, and permitted discharges. But the environmental question is still temperature. How warm is the river before the plant? How warm is the water after the plant? How much heat can be added without crossing ecological limits? During a heat wave, three things often happen at once. First, the air is hot, so river water receives more heat from the atmosphere and cools less effectively at night. Second, drought or low rainfall can reduce flow, so the river has less volume to dilute heat. Third, electricity demand rises because people need cooling. The plant is asked to work harder at the exact moment the cooling environment is less able to accept its waste heat. That is the trap. The same heat that creates need also reduces capacity. It is not a dramatic trap, but it is deeply systemic. It is built into physics. Heat moves from hot to cold. If the cold side is not cold enough, the system loses its easy path. The hidden limit is not the visible flame of a fire or the visible flood on a street. It is a temperature difference, shrinking until a permit, a sensor, or an ecological threshold becomes decisive. The metaphor is a lung. A power plant breathes through its cooling system. It inhales cooler water or cooler air. It exhales heat. For decades, the lung could breathe deeply because the outside world provided enough coolness. In a heat wave, that lung becomes constricted. The plant can still breathe, but not as deeply. It must slow down. The consequence travels outward. A reactor reduces power. The grid loses some supply. the market adjusts. Other sources fill the gap if available. Prices may rise. Operators manage reserves. Consumers may never notice directly, but the system has paid a cost. And if the heatwave is broader, that cost may not remain isolated. Neighboring countries may also have high demand. Hydropower may be limited by drought. Wind may be weak under stagnant high pressure. Thermal plants elsewhere may face their own cooling constraints. Transmission lines may operate under heat stress. Railways may slow trains. Roads may soften. Data centers may consume more power for cooling. Hospitals may receive more patients with heat stress. The energy event becomes one layer inside a larger heat emergency. This is why the mechanism has to pass through people. Imagine an elderly woman in a top-floor apartment during a hot night. Her building stores heat like a brick oven. The daytime maximum matters, but the nighttime minimum decides whether her body recovers. If the night stays above 20 degrees Celsius, and especially if humidity is high, the body's cooling system becomes less effective. Her fan moves warm air. Her refrigerator works harder. The care worker who visits her is delayed by transport disruption. The hospital nearby has more heat-related calls. The hospital also needs stable electricity to keep wards cool and equipment running. That electricity may come partly from nuclear plants that now face river limits, so the path is not abstract. Heat moves from atmosphere into city walls, from walls into bodies, from bodies into hospitals, from hospitals into the grid, from the grid into power stations, and from power stations back into rivers. The loop closes. Or imagine a farmer downstream. The river is not only a cooling channel for a power plant. It may also be part of irrigation decisions, livestock watering, local ecology, recreation, or regional identity. When water restrictions tighten, the farmer sees heat as an agricultural problem. When a reactor reduces output because the river is hot, the grid sees heat as an energy problem. When fish struggle, biologists see heat as an ecosystem problem. But it is the same heat moving through different doors. That is the hidden complexity. A river valley is not separated into energy, farming, ecology, and health in real life. Those categories are administrative. The river is continuous, so are the consequences. This is why good reporting must avoid cheap fear. A nuclear plant reducing power because of hot water is not the same as a nuclear accident. It is not evidence that reactors are about to melt down. It is not proof that electricity will vanish. But it is evidence that a hotter climate can reduce the reliability of water-dependent energy systems during precisely the periods when society needs electricity most. That is serious enough, without exaggeration. The facts are sufficient. The mechanism is sufficient. The image of a powerful reactor waiting on a warming river is sufficient. France has seen versions of this warning before. The summer of 2003 is the historical shadow behind every European heat story. That heatwave killed tens of thousands across Europe and forced governments to confront how deadly heat can be when societies are not prepared. In France, it became a national trauma, especially because so many elderly people died during a period when the danger was underestimated. It also showed that heat is not only a weather condition, it is an institutional test. Who checks on isolated people? Who keeps hospitals cool? Who warns the public clearly? Who adapts working hours? Who maintains water supply? Who protects crops and animals? Who keeps the grid stable? Since then, Europe has built heat action plans, warning systems, and public health protocols. But the climate has kept moving. The heatwave of 2022 added another layer. France faced intense heat, drought, low river flows, and major energy stress. Some nuclear plants had to reduce output because of river temperatures. In certain cases, the regulator temporarily adapted thermal discharge rules to maintain electricity security, while requiring monitoring. That kind of exception reveals the structure of the trade-off. In normal conditions, environmental limits protect rivers from excessive heating. In extreme conditions, the electricity system may need output badly enough that authorities consider temporary flexibility. But flexibility does not make the heat disappear. It reallocates risk. If a plant keeps running under modified rules, the grid gains electricity, and the river receives a heavier thermal burden. That may be justified during a severe grid security issue, but it should not be mistaken for a permanent solution. A rule can be adjusted. Biology cannot be negotiated with in the same way. Fish, oxygen, algae, and river food webs respond to physics and physiology. They do not care whether the paperwork was urgent. This is the uncomfortable precedent. When heat waves were rare, exceptions could remain exceptional. When heat waves become more frequent, the exception starts to look like part of the operating model, and that is where the future becomes harder. A system can survive occasional stress by using reserves, exemptions, imports, demand response, and emergency procedures. But if the stress becomes routine, emergency tools become normal tools. Then the system must be redesigned, not merely managed. Researchers have been warning about water-dependent energy infrastructure in a warming climate for years. Studies on future nuclear availability have examined how changing river temperature and flow can affect plants located on rivers. The exact results depend on site, design, emissions pathway, adaptation, and regulation. But the direction of concern is clear. Climate change affects both water quantity and water temperature. Those changes can affect power plants that depend on water. This is not a speculative movie plot. It is a measurable operational issue already appearing during real heat waves. The present event is therefore not isolated. It is part of a lineage: 2003, 2006, 2022, 2025 warnings, and now another early intense heat event, pushing the same question back into the grid. What is different now is the timing and the baseline. Meteo France reported that June 2026 was the hottest June on record in France. A June heatwave is not the same as an August heatwave in planning terms. June is earlier in the season. Rivers, soils, agriculture, school schedules, labor patterns, and tourism systems may not yet be in full late summer emergency mode. If the early season is already breaking records, the seasonal risk window stretches. The calendar becomes less reliable. Infrastructure designed around old seasonal assumptions begins to face stress outside the expected period. That matters for maintenance. Power plants often schedule maintenance around expected demand patterns. Grid operators plan seasonal availability. Farmers plan planting and irrigation. Health agencies prepare alert phases. If extreme heat arrives earlier, lasts longer, and repeats more often, the planning calendar is no longer just a calendar. It becomes another vulnerable system. The history also shows that electricity, security, and climate adaptation cannot be separated. France's nuclear fleet has long been presented as a low-carbon backbone, and in climate mitigation terms, nuclear power can produce large amounts of electricity with low direct carbon emissions during operation. That is one reason many energy planners include nuclear in decarbonization pathways. But low carbon does not mean climate-proof. A technology can help reduce emissions and still need adaptation to the warming already locked into the system. That nuance matters. The debate often collapses into slogans. Nuclear is either salvation or danger, future or past, clean or unacceptable. But the river does not care about slogans. The river asks a narrower question: how much heat can be added today? The answer may be compatible with nuclear power in many conditions, especially with proper design, cooling towers, coastal siting, improved forecasting, operational flexibility, and strong environmental rules. But the answer is not infinite. And the fact that it is not infinite is the whole point. The hidden limit is not ideological, it is thermal. The small weak point in this story is not small because it is unimportant. It is small because it is easy to overlook. A temperature limit in a discharge permit, a low flow threshold in a river, a few degrees of water temperature, a condenser efficiency curve, a nighttime minimum, a weather pattern that refuses to move. These do not look like the grand levers of civilization. They do not appear in campaign speeches as often as energy independence, national sovereignty, or industrial strategy. But they can decide whether a reactor runs at full power during a heat wave. The weak point is the right to release heat. That sounds almost absurd until the viewer understands what a power plant is. A power plant is not just a machine for making electricity. It is a machine for moving heat. It concentrates heat, extracts work from part of it, then rejects the rest. In that sense, every thermal power plant is asking the environment for a service. Please take this heat. For a long time, that service was treated as background. Rivers took heat, air took heat, oceans took heat, the atmosphere took emissions, forests took carbon, wetlands absorbed floodwater, snowpacks stored winter precipitation. The natural world acted as a hidden balance sheet for industrial civilization. Climate change is what happens when that balance sheet is overdrawn at planetary scale. Hot rivers are one local line item. They show that the environment is not an infinite sink. The communities most exposed are not always the ones standing closest to the reactor fence. Some live in cities where heat becomes deadly because apartments are poorly insulated, air conditioning is scarce or expensive, and nights remain hot. Some live in rural areas where water restrictions affect crops and livestock. Some work outdoors on construction sites, farms, delivery routes, rail yards, and roads where heat safety rules can reduce hours and income. Some are hospital patients whose survival depends on cooling, refrigeration, electronic monitoring, and staff capacity. Some are elderly people in care homes. Some are low-income families who cannot simply turn up cooling without fearing the bill. For them, electricity is not an abstract commodity. It is a chain of protection. When heat strains generation, prices, and infrastructure, vulnerability follows the chain. The same event can be minor for one household and dangerous for another. A wealthy household may absorb higher electricity costs and maintain indoor cooling. A poor household may ration cooling or live in an overheated building. A hospital may have backup systems, but backup systems still require maintenance, fuel, staff, and planning. A data center may have redundant cooling, while an elderly resident has only a window that opens onto hot air. This is why the headline number cannot explain the full danger. 4.1 gigawatts matters. But vulnerability is not measured only in gigawatts. It is measured in who has alternatives. The grid may be secure in the technical sense and still leave people exposed in the social sense. A secure grid does not automatically mean every home is safe. A stable wholesale market does not mean every person can afford cooling. A reactor operating within limits does not mean the river ecosystem is unstressed. A temporary reduction in output does not mean the broader system has adapted. The human layer makes the story heavier because it shows how physical limits become social outcomes. Heat moves through inequality. It finds the apartment without insulation, the worker without shade, the town with aging water pipes, the hospital with limited surge capacity, the farmer at the end of an irrigation allocation, the river reach already stressed by pollution or low flow. Infrastructure vulnerability is rarely about one giant failure point. It is often about a small component that everyone assumed would hold: a transformer overheating, a rail buckling, a pump station losing power, a culvert too small for new rainfall extremes, a cold chain interrupted, a hospital cooling unit failing, a river temperature permit being reached. In this story, the small component is the cooling margin. That margin is created by water temperature, river flow, plant design, and regulation. When it narrows, the electricity system must compensate. Compensation is possible, but it has costs. Other plants may ramp, imports may rise, demand response may be triggered, prices may move, maintenance schedules may be adjusted. Renewable generation may help, especially solar during hot, sunny afternoons. But solar drops in the evening, precisely when buildings may still radiate heat and people return home. Storage can help if available. Transmission can help if neighboring systems have spare power. But during regional heat waves, neighbors may be under stress too. This is why resilience cannot be built from one technology alone. It has to be built from diversity, efficiency, demand management, storage, grid reinforcement, water planning, building retrofits, and realistic climate assumptions. The most fragile point may be the assumption that the past is still a good guide. If planners assume heat waves will behave like historical heat waves, they may underestimate simultaneous stress. They may see river heat as a rare nuisance rather than a recurring constraint. They may see air conditioning demand as a comfort issue rather than a health and grid issue. They may see environmental limits as paperwork rather than protective boundaries around living systems. They may see June as early summer rather than a month capable of producing record national heat. A hotter climate turns assumptions into liabilities. That is the deeper vulnerability. It is not only that a river warms. It is that institutions may be slower to update than the river. By the time a threshold is crossed in the physical world, the planning world may still be debating whether the old categories apply. And in extreme heat, slow recognition is dangerous. Heat kills quietly. It does not always break windows or knock down buildings. It accumulates in bodies. It thickens the night. It turns medications, dehydration, age, heart disease, isolation, and poor housing into risk multipliers. It also accumulates in infrastructure. It warms rails, roads, cables, cooling water, soil, reservoirs, and buildings. The power plant beside the river is only one visible node in a larger accumulation. This is why the French nuclear story should not be reduced to an argument about whether nuclear power is good or bad. The real lesson is broader. Every energy system has an environmental dependency. Fossil fuel plants need fuel supply chains and often cooling water, while also producing greenhouse gases that intensify the heat problem. Hydropower depends on river flow and snowpack. Wind depends on weather patterns and transmission. Solar depends on land, materials, grids, and storage or flexible demand. Nuclear depends on fuel, safety systems, skilled operators, regulation, cooling, and long-term waste management. There is no energy source outside the world. The question is not which source is magic. The question is how to build a system whose dependencies do not all fail under the same stress. Heat is dangerous because it is a common mode stress. It touches many parts at once. It raises demand. It warms rivers. It lowers thermal efficiency. It stresses workers. It increases wildfire risk. It can reduce hydropower. It can increase air pollution. It can strain health systems. It can reduce labor productivity. It can damage infrastructure. It can push agriculture into irrigation demand at the same time that rivers are low. Common mode stress is what turns a weather event into a systems event. This is the larger pattern behind the French reactors. The atmosphere is not simply producing hotter days. It is revealing dependencies that were easier to ignore in a cooler world. A hot river is a message from that larger pattern. It says the energy transition cannot only be about replacing carbon molecules with electrons. It must also be about the conditions under which those electrons are produced, moved, stored, and used. Electrification is essential for reducing emissions in transport, heating, and industry. But electrification also increases the importance of grid reliability during heat. If cars, heat pumps, hospitals, communications, water systems, and cooling all depend more heavily on electricity, then electricity becomes the central nervous system of adaptation. When the grid is strong, society can endure heat better. When the grid is strained, heat becomes more dangerous. That means climate mitigation and adaptation are no longer separate chapters. They are the same book. A country may build low-carbon generation to reduce future warming, but it must also make that generation resilient to the warming already happening. For river-cooled nuclear plants, resilience may mean better forecasting of river temperatures, operational planning around heat waves, upgrades to cooling systems where feasible, more flexible demand, larger reserves, stronger transmission, careful water governance, and a grid mix that does not depend on every thermal plant running at full output during peak heat. It may also mean hard choices about where future plants are sited. Coastal plants may have access to larger cooling bodies, but coasts bring sea level rise, storm surge, corrosion, and marine heatwave issues. Inland plants may avoid coastal hazards, but depend on rivers that can warm and shrink. Cooling towers reduce direct river heating, but use water through evaporation and can face performance limits in hot, humid air. Dry cooling reduces water dependence, but can be less efficient and more expensive, especially during heat. Every option moves the constraint. None abolishes physics. That is why the future cannot be planned with slogans. It must be planned with site-specific hydrology, climate projections, ecology, engineering, economics, and public trust. Public trust matters because during heat emergencies, people must believe the information they receive. If officials say a reactor reduction is environmental, not a nuclear safety accident, the distinction must be clear. If grid operators say supply is secure, people need to understand that secure does not mean unstressed. If regulators allow temporary exceptions, the public needs transparent monitoring and an explanation of why the choice was made. Without trust, every technical decision becomes fuel for rumor. And rumors flourish during heat because heat creates anxiety. People feel trapped in their bodies and homes. They look for simple causes. They may blame one technology, one party, one company, one country, one conspiracy. The actual story is harder but more useful. A heat wave pressed on a river, the river pressed on environmental limits. The limits pressed on nuclear output, the output pressed on grid management. The grid existed inside a broader heat emergency. That chain is not simple, but it is knowable. And knowing it is the first form of adaptation. The new baseline question is the most unsettling part of the story. A baseline is what people call normal without thinking. Normal river temperatures, normal seasonal flows, normal peak demand, normal plant availability, normal maintenance windows, normal heat warnings, normal hospital capacity, normal sleep in summer, normal fish survival, normal electricity prices. Climate change does not only create extremes above normal, it changes the normal around which extremes form. When the baseline rises, a heat wave does not need to be meteorologically impossible to become operationally dangerous. The same weather pattern that once produced a difficult week can now produce a record week because it begins from a warmer world. World Weather Attribution has repeatedly emphasized that human-caused warming has made European heat waves hotter and more likely, and its analysis of the recent event placed the heat in that wider climate context. That does not mean climate change invented every high-pressure system. It means the dice are loaded toward higher temperatures when those systems occur. This distinction is important. A blocking high-pressure pattern can happen naturally. Hot air can move north from North Africa naturally. Clear skies can allow strong solar heating naturally, but the background atmosphere is warmer because greenhouse gases have trapped more heat. So when the pattern appears, the resulting temperatures ride on top of a higher platform. The mechanism is like raising the floor in a room. The ceiling may be the same height, but everyone inside is closer to hitting their head. The atmospheric pattern is the jump. Climate change is the raised floor. In France, that raised floor means a June heatwave can push national averages into record territory. It means rivers can start closer to operational limits. It means nighttime recovery can fail more often. It means demand for cooling can rise earlier in the season. It means systems designed for past distributions experience more time in the tail. A new baseline does not announce itself with one final disaster. It appears through more frequent disruptions that are individually manageable, but collectively transformative. A train slowed here, a hospital surged there, a power plant derated, a school closed, a wildfire warning raised, a water restriction imposed, a farmer changing planting decisions, a household buying an air conditioner, a grid operator revising forecasts. Each event can be explained locally. Together, they describe a world moving out of its old envelope. The French reactors facing hot rivers are one chapter in that movement. They show that even low-carbon infrastructure can be vulnerable to climate impacts. They show that adaptation is not optional. They show that environmental protections may become more contested as heat pushes electricity demand upward. They show that water policy and energy policy are the same policy during extreme heat. They show that thermal pollution once treated as a local regulatory issue, can become part of national energy security. And they show that the natural systems supporting modern infrastructure are not passive. Rivers do not vote, write laws, or speak on television, but they enforce limits. They enforce them through temperature, flow, oxygen, ecology, and physics. A hot river is a kind of veto, not total, not permanent, but real. The danger is not that France suddenly cannot produce electricity. The danger is that the margin between reliable production and environmental stress becomes narrower during the very events that make electricity most necessary. That is a planning problem, an engineering problem, an ecological problem, and a social problem at the same time. It cannot be solved by pretending one layer does not exist. If environmental rules are ignored, rivers suffer and ecosystems weaken. If electricity needs are ignored, people suffer during heat. If climate trends are ignored, both crises return with less warning. The only serious path is to design for the conflict before it arrives. That means reducing heat-trapping emissions to limit future warming. It means adapting infrastructure for the warming already here. It means insulating homes so survival does not depend only on air conditioning. It means designing cities with shade, ventilation, reflective surfaces, and cooler public spaces. It means protecting vulnerable people before emergency rooms fill. It means managing water as a shared stress point across energy, agriculture, ecosystems, and drinking supply. It means building grids that can handle high cooling demand without relying on one fragile assumption. It means treating forecasts not as background weather reports, but as operational intelligence for the whole society. There is also a psychological adaptation required. People need to stop imagining climate change only as disaster images from somewhere else. A burned forest, a flooded street, a hurricane landfall. Those images matter, but climate change also appears as an administrative constraint inside a wealthy country's power system. It appears as a reactor output notice. It appears as a river temperature reading. It appears as a grid operator reassurance. It appears as a hospital heat plan. It appears as a water restriction map. It appears as a household deciding whether to pay for cooling. This quieter form may be more important because it shows how deeply climate enters normal life. It does not always knock the system down. Sometimes it makes the system operate with less freedom, less spare capacity, less ecological room, less time to recover, less certainty that old plans apply. That is what should remain after the event passes. The heat wave will eventually break. Cooler air will move in. River temperatures may fall. Reactors may return to normal output. Wholesale prices may settle. The news cycle may move to another emergency. But the lesson should not cool as quickly as the river. The lesson is that the hidden limit has been visible for years, and it is becoming more relevant. In 2003, Europe learned that heat kills people. In 2022, Europe learned that heat and drought can collide with energy security. In 2026, France is being reminded that even a powerful nuclear fleet depends on environmental conditions that are changing. The system is not doomed, but it is exposed. There is a difference. Doom says nothing can be done. Exposure says the weak points must be found before they are tested again. The weak point here is not glamorous. It is not a spectacular explosion or a dramatic blackout. It is the cooling margin between a reactor and a river. But civilization often turns on such margins. The distance between a city street and a flood is the height of a curb and the capacity of a drain. The distance between a crop and failure is a planting window and a few weeks of soil moisture. The distance between a heat wave and mass death is nighttime cooling, social care, and working electricity. The distance between full nuclear output and reduced nuclear output can be a few degrees in a river and the flow needed to carry heat downstream without crossing ecological limits. Small margins decide large outcomes. That is the architecture of risk in a warming world. The truth and falsehood must be separated carefully. It is true that hot rivers can reduce nuclear output in France. It is true that EDF has had to adjust production during heat waves, because of environmental temperature limits. It is true that Meteo France recorded an exceptionally hot June, and that extreme heat increases both cooling demand and stress on water systems. It is true that climate change makes European heat waves hotter and more likely by raising the temperature baseline. It is true that nuclear power, like all thermal power, must manage waste heat. It is true that river ecosystems can be harmed by excessive warming, especially when flows are low and oxygen levels are stressed. But it is not true that every reduction in reactor output means a nuclear safety emergency. It is not true that one heat wave proves the entire French nuclear system is failing. It is not true that nuclear power uniquely depends on the environment, while other energy systems do not. It is not true that climate change alone determines every operational decision at every plant. Maintenance, market conditions, plant design, grid demand, river flow, regulation, and weather all interact. It is also not honest to claim that because the grid remains secure, there is no problem. A system can remain secure and still be warning its operators. A person can remain standing and still be dehydrated. A bridge can remain open and still need inspection. A river can continue flowing and still be too warm to absorb more heat safely. The real risk is cumulative. More hot days, more warm nights, more low flow periods, more simultaneous demand across regions, more competition for water, more frequent decisions between ecological protection and electricity output. More reliance on electricity for cooling as summers grow harsher. That risk can be managed, but only if it is named. When people argue about this event, some will use it as proof that nuclear power has no future. Others will use grid stability as proof that concerns are exaggerated. Both shortcuts miss the mechanism. Nuclear power may remain part of a low-carbon grid, but it must be planned for a hotter water cycle. Grid operators may handle individual heat waves, but repeated constraints can change reliability economics. Environmental protections may seem inconvenient during emergencies, but they mark real ecological limits. The serious conversation begins when all of those statements are held at once. A mature society does not choose between physics and politics. It lets physics discipline politics. It asks what the river can bear, what the grid needs, what people can survive, and what design changes reduce the conflict next time. That is the opposite of panic. It is seriousness. It is also more frightening than panic because it admits the problem is structural. A panic ends when the siren stops. A structural problem waits for the next hot week. The final image is not a dark city. It is not a reactor in crisis. It is a river passing a nuclear plant under a brutal summer sky. The water still moves. The plant still stands. The transmission lines still cross the fields. Nothing in the image says collapse. That is exactly why it matters. The world is not always transformed by one dramatic failure. Sometimes it is transformed by a familiar system becoming conditional. It works, but only if the river is cool enough. It works, but only if the night releases heat. It works, but only if the grid has spare supply. It works, but only if the environmental margin is not exhausted. It works, but the old climate made those ifs easier to ignore. The new climate writes them in larger letters. France's hot rivers are not just a French problem. They are a preview of the kind of limits that appear when industrial systems meet a warmer planet. Cooling water is the hidden limit because it sits between the machine and the living world. It is where physics becomes policy. It is where climate becomes electricity. It is where a river becomes part of national security. The event will pass. The reactors may return to normal. The headlines may fade. But the thing revealed by this heat will remain. Modern infrastructure was built with nature in the background, and now the background is moving to the front of the story. The question is not whether France can get through this heat wave. It probably can. The question is how many systems around the world are already depending on a kind of coolness that the future is quietly taking away.